Yes.
Okay, so good afternoon, evening, morning, everybody. It's a pleasure to be here. Let me give you a rundown, a leisurely rundown of what I hope to achieve in this talk, or at least to discuss. You see the well-known Navier-Stokes equations in the box at the top of your screen, and I'm simply going to deal with incompressible, a box domain, an L-cube domain, periodic, with a standard problem. And I want to discuss intermittency and its consequences, which is a very old problem. And when I switched subjects in the 1980s, I got bored with working on things like solitons, and I got interested in turbulence. I started to read around, and I read Batchelor and Townsend's 1949 paper. Now, this is a very old paper, and you have to consider the context. It was only 4 years after the end of the Second World War. Townsend's laboratory was like full of war surplus equipment, like old oscilloscopes and rubber wires and this sort of thing. So it's a rather remarkable paper in many ways, because I may not be correct here, but I think they were the first to discuss and introduce the idea of intermittency in the sense that we understand it, that they insisted that turbulent flows, particularly in the wind tunnel data they were talking about, was not a Gaussian sea, but they observed this sort of clustering of wave numbers and frequencies that we think of now of intermittency, and which showed up in their data in things like the signals processing measures of things like flatness being much, much larger than would normally be expected for a Gaussian sea. And so my thinking was really formed by this paper, and also 10 years later, in reading Uriel's book on the multifractal approach to turbulence. And by the way, Uriel, it's 6 days late, but I would like to offer my congratulations on your 80th birthday. I didn't get the chance to add it amongst all the others who were wishing you well 6 days ago. But reading your work on this has been the other formative part of my education. Now, I want to discuss this as a sort of an amateur analyst would look at it, and think of it this way. That's the way I want to approach it, but informed by computations. You know, there's a generation now of computations of incompressible Navier-Stokes on a periodic cube, and they show the same typical intermittent behavior in vorticity, strain, in energy dissipation fields. And if I may just flip on and then come back to give the local guys some advertisement. This is a computation by Shamridi at ICTS and his now ex-student Jason Picardo. Jason is now at chemical engineering in IIT Mumbai, and this is a 512 cubed computation. You see on the left the energy dissipation field, and on the right what's called the Q field. If you go down here, the difference between the square of the vorticity and the strain. And this is sort of typical. We've seen these sorts of cubes before. You know, something like 50 years ago, there was a comedy film in Britain about an advertising agency, and it was called Every Home Should Have One. They were trying to sell some gimmick. Well, they should have done a follow-up film called Every Turbulence Group Has Got One, because most groups have got cubes of their data of this sort. And although they're all different in detail, they're typically similar. And if I go down, this is courtesy of Diego Donzis of Texas A&M. This is the 4096 cube database of theirs, Reynolds lambda 1000. And you can see here very much how vorticity dominates in tubes and the green on the outside where strain dominates just outside the tubes. It's shown up very nicely, but typically it's the same sort of behavior. So let me return. And so what we see is intense, normally if those are snapshots in time, but I think if it's too expensive to run as a film or a movie, but if you could, I think what you would typically see is in intermediate times, intense regions begin to flatten into like quasi 2D pancakes. Then the pancakes then roll up into tubular filamentary structures, and you get the fragmentation that we actually seen in those pictures. And I want to address in this talk how this visual manifestation of intermittency can be connected to Navier-Stokes weak solutions and invariant scaling. Because it's very well understood, I think, in a multifractal approach, but for an analyst looking at Navier-Stokes in particular, it's not so well understood, because analysts are confined to looking at spaces which are averages in cubes, and that's very much a sort of disadvantage. So let's move on. So there is a history of large-scale Navier-Stokes computations, and I don't want to go into any detail, and apologies to anybody I missed out, but I think I've got the big well-known computations going back to 72, going through history. There's 2 annual reviews here, Mohin and Mahesh, and Ishihara, Goto, and Kaneda, which is the most recent. And then number 8 is the one I've just shown on the previous slide, the 4096 cube computation. And then there are later ones done at Nagoya, Ishihara, Kaneda, Hunt, and others. The latest is an 8000 cube computation, and there's a paper just come out in Proceedings of the Royal Society. So let's do a little bit of mathematics. So here we've got Navier-Stokes in red, and I'm just going to do this formally because this is how we understand it. If you're going to do it properly, the French mathematicians way, there's a whole chapter of a book in doing things with weak solutions and proving convergence in a weak topology and all that, but I'm going to jump over all that. And so the straight energy equation is this one. And if we want to deal with the forcing, we break it up by Cauchy-Schwarz. That's easy to do. And I'm using this notation for the double bar as the L2 norm. And then I'm going to time average, and that's this bracket. So we time average, and we end up basically with this thing here on the right-hand side. Now that doesn't look very pretty, but then what you do is that you define your Grashof number, which is a measure of the forcing, okay, and a Reynolds number whose typical velocity is based on the average velocity field. Now, of course, the average velocity field after time t is a response to the forcing. So in a sense, Grashof has the forcing and Reynolds is the system response. But what you see is, of course, that this right-hand side here now is proportional to Grashof-Reynolds. And again, that's not so satisfactory because Grashof is a very, not a very physical thing until Doring and Foyash in 2002 showed that for Navier-Stokes solutions, it was actually for limited bandwidth of frequencies, but you can fix that. That for Navier-Stokes solutions, Grashof is bounded above by constant times Reynolds squared. And so that makes this, actually, the right-hand side is Reynolds cubed plus order Reynolds squared. And then if you do the usual, take a definition of inverse Kolmogorov length of capital E over nu cubed to the quarter, then you get an upper bound of Reynolds to the 3/4, which coincides with K41, everything that we know and love. But what we would like to, that's just the energy equation. what we would like to know in the Navier-Stokes sense, are there scales more smaller than this, and do those scales converge, or do they just keep going? Now, I pinched a picture out of Uriel's book, which is actually on the web, so I've downloaded it, about how you start with vortices, breaking up to 2 daughter vortices, breaking up to 4 ad infinitum. And of course, Richardson, in his 1922 book on numerical weather forecasting, he believed that viscosity halts the process. I don't know how many of you read Peter Lynch's book called Numerical Weather Forecasting, Richardson's Dream, but it's a very good book and I recommend you reading it if you haven't. And so the question really is do the length scales converge and become a finite limit, or do they go on forever? In other words, driving vorticity ever down to molecular scales. And then poetically, it's a question of whether Richardson's parody of Swift's poem is actually true or not. Is there a finite limit or not? Okay, so what we need to do as an analyst, one needs to actually get some sense of a cascade. Because a cascade is like a sequential process in time that involves vorticity and strain being driven down to ever smaller scales. And so the way I do it is this, is that I take the velocity field, take n gradients in the general sense, and put it to the 2mth norm, which is defined this way. Now, I think most of you are familiar with this, that this is a sort of notation that one can use. You can, m is 1 is the L2 norm, m is infinity is the sup norm or maximum norm, but you can take m as a continuum from 1 to infinity. And so in other words, you can zoom from L2 up to L infinity using this notation. Okay, now what I want to do is to non-dimensionalize that. So if I stick this in front, then my capital F labeled n for derivatives and m for the order of the norm, that's a dimensionless object, and it's a function of time. And very importantly, this alpha is defined this way, and that's going to crop up on it almost every slide. 2m over 2m into n plus 1 minus 3m. And so what we're thinking of is the derivatives you can think of as sensitive. The higher the derivatives you use, they're sensitive to ever finer length scales in the flow. And that higher values of m pick out larger spikes. You know, when you're getting m very large, then the largest spikes are the ones that are sort of like amplified. It isn't a wavelet, and I'm not pretending it is, but the principle is like one, is that one is in a sense zooming down to a scale and then taking the major features on that scale and amplifying it. That's really in a sense what this does. Okay, so if I reiterate this f is a function, these f's are functions of time, and they are dimensionless. And if you actually then look at Navier-Stokes scale invariance in the way that we know and love, then you find, surprisingly or not, that these f's are invariant. I suppose they ought to be because they're dimensionless, but they are. They're invariant under this transformation. And so basically the key thing that from this invariance is this alpha. That's where it comes from. Okay, so I have my first main result, and since we have a very mixed audience, I'm not going to give a proof of this. You can find it in this Journal of Nonlinear Science paper last year. So with this definition, and with m from 1 to infinity, with the m going from 1, sorry, for n greater than 1, with the m from 1 to infinity, and n is naught, m greater than 3, then basically this is a weak solution result because that's all we have for Navier-Stokes. Leray's weak solutions satisfy the time average of this F to this alpha, power alpha, is bounded uniformly by Reynolds cube, not uniformly in the constant, but there's not much I can do about that. It's bounded uniformly by Reynolds cube. It's a very clean, neat result. And in the next slide, if you say, well, I've never seen that before, well, there are parts of it that you have seen. For instance, now I have a table. If I chose n is 1 and m is 1, then that's exactly, you see, when n is 1 and m is 1, the alpha 1, 1 is actually 2. And so what there exactly have you got the Leray's energy inequality. But of course, this theorem is true for all that range of n's and m's. And so if I went through specific cases, n is 0, but m is infinity, so no derivatives, m is infinity, the time average of this is bounded by Reynolds cubed, is a result of Luc Tatar in 1978. If you go to, well, we've got n is 1 and m is 1, that's exactly Leray's result from 1934. When n is greater than 1, but m is 1, then you've got the result of Foyash-Guillaupe and Temam in 81. I think this was Colette-Guillaupe's thesis, actually, I think. I gave a talk on this in Paris on a meeting for Claude's 70-something birthday a few years ago. And Colette was in the audience and she said, well, you know, I'd almost forgotten about this result. And actually, this paper, it's in Communications in PDEs, and it was in 1981, and it fell between the cracks. And there's an awful lot of people who don't know about it. But actually, it's a very, very important result. But this is there. So essentially, all the well-known special cases are actually all in this theorem. But then you've got the whole continuum from for all n and m. Now, another special case I would like to mention is n is 1, and for higher m's, where this alpha 1m is now 2m over 4m minus 3. This cropped up before. I did some joint work with Diego Donzis and Anupam Gupta, who was Rahul's student, Bob Kerr and Dario Vincenzi, and we published 2 papers, one in JFM and one in nonlinearity. And we basically, we didn't know about this more general theorem at the time. We were just doing n is 1. And this in those papers is what we call DM. And we actually discovered that plotting numerically these DMs, they separate extremely nicely in descending order. As m increases, the plots in time of the DMs decrease. They do not cross one another. It was a very nice result. And as also, Bob Kerr used these DMs in his JFM 2013 paper, where he revisited computations on 3D Euler and actually found that these DMs as function of time, there was a critical time when they all crossed. And when he examined the behavior at that critical time, when they crossed, he discovered that the solutions did not become singular, but they actually became double exponential. So, you know, these are just sort of remarks on this particular result. So what I want to do, I want to use some of the consequences of this theorem later on. At the rate I'm going, I'm probably going to finish very early, but never mind. So are there strong solutions? Because these are for weak solutions. And weak solutions, as you know, we can't write them down, they're smeared out. You can only write them in the sense of average, in terms of averages against a test function, etc., etc. So we want to know, are there strong solutions and what would they look like? Well, you can prove, and it's in the same paper by myself, that the sufficient conditions for strong solutions to exist are that these Fs you need bounded not to the power alpha nm as you have for weak solutions. You need a factor of 2. And if you had for any pair nm greater than 1, if this were true, then strong solutions would exist. But that is a sort of sufficient condition. It's an if condition, and nobody has found any condition like this. But this is how the two are related. So the weak solutions are the ones that we naturally have and that appear all over the place. If we want strong solutions, then some bright person is going to have to prove the same result with a factor of 2. And I've cast all over the place looking to see how we could introduce this 2, and I have not been able to do it. Now, just as an aside, because I know there are a few analysts in the audience, if you were taught in Navier-Stokes analysis, then one of the things you would be taught way back to 1959 for Prodi and for 1963 for Serang, what's now called a Prodi, and then 1964 Ladezhinskaya, the Prodi-Serang-Ladezhinskaya condition for regularity, that basically says this, that if your U belongs to LP in time and then LQ in space, then for a strong solution to exist, a unique smooth solution, a strong solution, you need P and Q to obey this thing. 2 over P plus 3 over Q is 1, where Q is greater than 3. Well, how does this relate to this theorem above? Well, the answer is very simple. Take N is 0, pick P is 2 alpha naught M, and pick Q is 2M. Okay, you see, N is 0, so you need U in LQ, so you pick M, you pick Q in 2M, and exactly 2 over 2, and if you work out what this alpha is, it does exactly come to 1. So at the level of N is 0 and Q is 2M, this is exactly the Prodi-Serang condition, except you can see now it generalizes the whole Prodi-Serang conditions up to all derivatives. So everything that we know and love about Navier-Stokes are actually in these 2 theorems. So let's move on. So now let's try and define a sequence of length scales. Let's try and extract some physics out of this. Excuse me while I have a sip of water. So what I'm going to do now is examine these things which I call H, n derivatives to 2m. And, you know, you've got basically a length to the minus n times the 2m, and then you've got a length cubed. Well, what I'm going to do is say, define, this is a definition, take lambda as a length and look at what the dimensional analysis of this thing is. Okay, now you've got a time to the minus 2m in here because of the u, so you're going to need a nu to the 2m. And then I'm going to need this amount of lambdas, ignore this red, to basically work out what the dimensions of this thing are. When you do that without the red, it gives the wrong answer. And I spent weeks on this, sort of banging my head against the wall, wondering. And then when you put n is 1 and m is 1, which is at the level of basically the energy inequality from which you should get the Kolmogorov length, it gives the wrong answer. And then I realized that I was basically getting my definition wrong, because of course, when you look at the averaged energy from Laray's energy equation, it's energy per unit volume. And the per unit volume need an L to the minus 3. But if you've got an L there, then you need to rescale it with a lambda. And when you put that back in, and then you unstitch this for lambda, then exactly it's going to give you the right answer for n is 1 and m is 1. And when you unstitch that for lambda, it simply gives this very nice relation L lambda to the -1 to the n plus 1, and it comes out to be exactly these Fs that we've had in the last two slides. Okay, so with this alpha, which we have in the previous theorem, basically what you can then prove, it's really, when I say lemma, it's really a corollary of the weak solution theorem. For weak solutions, we use that theorem and we find that the average of L over lambda is basically bounded above by Reynolds to the 3 over n plus 1 alpha. And when you put n is 1 and m is 1, that gives you exactly 3/4, which it should do. Well, that's the Kolmogorov length. But now we can hold n fixed and increase m, or we can hold m fixed and increase n. And now we've got a whole continuum of scales here for continuum of n and m. What we would like to know is, what we would like to know is there a limit? As you increase n and m, particularly n, does it just basically go to infinity? And the answer is no, it doesn't, because of this n plus 1 basically over that thing. And basically in the large limit, you basically goes to 3. So there is a finite limit, and in that sense, Richardson and Kolmogorov were correct. There is a finite limit. The only problem is that whereas you've only got a finite range of scales between the Kolmogorov length running at about 1 millimeter and mean free path running at 50 nanometers. So you can't take your Reynolds number too high, or you'll basically get even though this may have a finite limit, you'll get your upper bound basically to be so large that it will go below this level. But in principle, there is a finite limit. Okay, so now let's move on. Now I want to move on to the last section of what I'm doing. And I was, in my reading, when like I say, I switched subjects in the mid-late 80s, I read Uriel's paper with Fournier on the idea of turbulence in d dimensions, where d is no longer an integer, but restricted to d greater than 2, and they did this by analytically continuing the Taylor expansion of the energy spectrum. But of course, the idea of non-integer dimensions has taken root in this vast array of papers on the beta, the bifractal and multifractal models, and they're of course all outlined in Uriel's book, but this is sort of where I got the idea from. So my question as a Navier-Stokes analyst is, can Navier-Stokes estimates be found on the domains of non-integer dimension? Well, in the fully rigorous sense, the answer is a definite negative. For instance, I don't think we have any proofs of the divergence theorem or Stokes' theorem on fractal domains, nor do we have any proofs of Sobolev inequalities on fractional domain, on fractal domains. So none of the tools that we need to use to sort of explore solutions are available. But nevertheless, the answer, the question persists. So I'm going to ask it. And I'm going to look now, that made me do the following calculation. So far we've got all our results are in a 3D domain. So can we generalize it to a d-dimensional domain, but keep d as an integer, 1, 2, and 3? Excuse me. And of course, two-dimensional Navier-Stokes is 2D Navier-Stokes as it is in 3. In 1D, it's really Berger's equation because there's no pressure and there's no div u. But I'm going to now generalize my definition of my invariant dimensionless f, and I'm going to call it FMD. And so now the appropriate definition for that, now all that changes is the alpha. And what changes in the alpha is that what was a -3 is now a -d. And then all the other properties of non-dimensionality and invariance go through. And then if you have to do quite a lot of work, but for D's 2 and 3, it's essentially the same theorem as before, that we have the estimate of FNMD. It's not just to the alpha NMD, but you need a 4 minus D in front. You've just got to work it out. And I was a bit surprised by this and had to go over things many times to be sure. But it's definitely a 4 minus D, which of course simply becomes unity when D is 3. And then the same result holds when D is 1 if you do this for Berger's equation. So what you're going to end up with is a 1 for D is 3, a 2 for D is 2, and then you're going to have a 3 when D is 1. Okay. Now, what this theorem does here, it shows you how the exponent of FNMD scales with D. And we've got this, as I've said before, rather surprising 4 minus D in front in the exponent. Now, when N and M is 1, okay, essentially this, for all D, what you find is that this factor of 4 minus D, it just simply cancels because the denominator of alpha 1, 1D actually is 4 minus D. So this 4 minus D cancels. And it gives us the correct bound on the average energy dissipation rate. Now for D is 2, of course, what this gives you is a factor of 2. And there exactly is that factor of 2 that we needed in that strong solution theorem. Like I said earlier on, the weak solutions is F to the alpha. For strong solutions, you would need a factor of 2 in there. Well, there's your factor of 2. So what it's saying is that for D is 2 or less, you actually do achieve that theorem. Well, of course, that's a well-known result that you don't really achieve proper regularity until the dimension comes down to 2 or less. Well, here it's exactly displayed in this 4 minus D. And so the D is 2 case is critical for regularity. Okay, so let's move on. So let's look at, this is actually my last slide. So I'm going to look now at the following. Take a look at the exponent of this FMD. If I may just go back up, you see there is this exponent. Now this is very important. Okay. Now, the formula poses the obvious question. Could this theorem be true in D in non-integer dimensions? Everybody I've shown this to asked me exactly this question before I've even posited it. And as I've said explicitly, we don't possess any technical methods to prove this. But I think I've come to the conclusion that perhaps it's the wrong question to ask. And the reason is, I think it's probably my age, that somebody of my generation and older, we're too used to thinking in terms of things like the Lorentz equations, where solutions asymptote to this well-known wing-shaped attractor that sits in a 3 space, and it has a dimension of, 2.05, 2.06, depending on your definition of dimension. We're too used to thinking of dynamical systems in those terms. But there really is little evidence to suggest the existence of such an attractor inside Navier-Stokes, although one, of course, cannot discount it. I think it's better to look at it this way. Let me go back up here now. I think it's better to look at it this way. If we think of the cubes, Shamridi and Jason's cube or the Texas A&M cube, they all manifest the same tendency towards fragmentation, filamentation, and to get there is these local iterations of flattening and filamentation. It may go through several iterations. And it may indeed be impossible to assign a single spatial dimension to this whole process. But if we did so, the trend towards flattening and filamentation suggests that the dimension is decreasing with time as you're coming down from like pancakes down to filaments. And then if you even run a computation further, and the Hunter-Nell single one on 8,000 cube begins to show the filaments even beginning to break up into pieces. So we're thinking there is evidence that the dimension is decreasing in time. So now look at this formula and ask yourself the question, let's decrease d. What does it do? Well, actually, this formula, which is my exponent of f, it increases as d decreases. Okay, and an increasing exponent, okay, it lies in the direction of more regularity, not less. It's more regularity, the bigger the exponent. Now, in physicist language, this essentially means that you're going in the direction of more dissipation, not less dissipation. So I suggest that this indicates that the flow might be adjusting itself to find the smoothest, most dissipative set on which to operate. Okay, now this runs counter to the commonly held view that sort of viscous turbulence is sort of like ruled by local singularities as being long-standing candidates as the underlying cause of turbulent dynamics. I accept that for the Euler equations. I think that's probably correct. But for Navier-Stokes, I would suggest that this evidence here says that it's the opposite direction, and that you get these fragmentation in these cubes because the flow is trying to find the most dissipative, the most regular set that it can find, and that's why it looks that way. I think that's a point for debate, but I think I'm going to stop there, Alan. So over to you.
Well, thanks so much, John. That's a very inspiring talk. Lots of interesting remarks. Are there questions for John? Yeah, someone is clapping. I should clap also myself. That's I share that view.
If you give me a moment, I need to
Uriel,
turn my...
Uriel is raising his hand.
Right.
Uriel.
Yes. Thank you very much. It was a very clear picture. I would assume that one can divide in principle a numerical simulation which can falsify or confirm your conjecture. So what do you have to say on this?
Well, Uriel, as you know, I'm not a numerical man, so I would need advice on how it would be done before I could actually make a serious comment.
But okay, you know a lot of people, and at least you can speculate at the theoretical level what would be needed.
Yes, I'm not sure numerically. I mean, I'm putting this out here and I'm asking you, how would one numerically look for a most dissipative set numerically?
Good question. Yeah, you have to rephrase it a little bit. Yeah.
No, I think you've asked a good question there, but I think I would have to plead ignorance, or at least I would need advice from friends as to how this could be done.
Well, you always have the right to sort of a dream of something crazy, and people, if it's crazy, people will tell you. That's always a possibility. Okay, we have a question from Rahul. Do your method apply to stochastically forced Navier-Stokes equation?
Now, the specific answer is I don't know, but my suspicion is probably not. I would, my colleague Martin Heira is 2 offices up from me on this, we live on the same corridor. And if we were back at Imperial, I would wander along the corridor and ask him. But unfortunately, that's not possible at the moment.
Okay, so a question to ask to somebody. Bérangère asked, well, so rather she said, I have a comment about the link with multifractal. So I guess, Bérangère, if you want to unmute yourself.
Yes, hi, John.
Hi.
Thank you for this talk. As you know, I'm among the people who try to see if your last possibility is true or not. And I have a comment about the implication of your result view from the multifractal case. As you know, some time ago, Paladin and Vulpiani, they devised a kind of theory stating that in case the field is multifractal, what is the equivalent of a Kolmogorov scale as a function of h?
Yeah.
And the result is that it scales like eta h equal Reynolds minus 1 over 1 plus h. Okay. So you see, as h goes toward minus 1, this goes larger and larger. And your bound, if I understood it well, it says that the scale cannot decrease faster than Reynolds to the minus 3. And if it's true, if my computation is correct, it means that this would prove that in the multifractal spectrum cannot have exponent smaller than minus 2/3. Is it correct?
Well, yes, I can see. Then the question, a deeper question arises is how valid is it to compare a result from Navier-Stokes analysis to the multifractal analysis? I mean, of course, one should compare. The question is, are we comparing like for like? It's these I say are weak solutions, and weak solutions are not unique, and that's a big problem. It would be so much easier to answer your question if we had a theorem on strong solutions, but we don't. And this is maybe this lack of uniqueness is where the problem in comparing matters actually occurs.
Well, I don't see why it's related to lack of unicity. I thought it was just a nice bound on multifractal spectrum that we could compute from intermittency.
It could be if you allow the comparison. If you see what I mean. You see, the problem is, it's a question of whether I'm wearing an analyst hat or a physicist hat. If one wears if one wears a physicist hat, if one wears a physicist hat, then I agree with you.
Okay. So that's quite interesting. In fact, I think you should stress in your paper and in your presentation, because
well, I will reread the Vulpiani and Paladin paper because I do have it. Yes.
Yeah.
But thank you for the comment. That's really very interesting.
Okay, very good.